Hi, I'm Professor Kelly, and this is a lecture on environmental hazards for CSCI through 8 Programming Language Design. By environmental hazards, I don't mean oil spills or earthquakes. I mean hazards in the programming environment that can be created by the combination of permissive compilers or interpreters and bad code. The learning goals for this lecture are to define alias, side effect, dangling reference or pointer, and memory leak, to explain how each hazard affects memory, and identify environmental hazards in the code. An alias is when a memory location has more than one name. Aliasing occurs all the time in programming. Any language with pointers or references has aliasing. In Java, for example, h2 equals h isn't creating a second house. Instead, we are creating a second name for the same house. One house on the heap with two different names pointing to it, h and h2. In C or C++, we can use int star to create the pointer w. We can assign w to the data stored in Z. Now the data stored in Z has two names, Z and W. Aliases are dangerous because of side effects. Let's define side effect. A side effect is when a change escapes the current code running. Side effects occur all the time in imperative languages, and not so often in languages like Prolog or Haskell. They include a change to memory, such as a change to what's stored on the stack. If int z equals 2 is in a function, that is information being put on the stack. Painting a house blue would be modifying the heap. Both of these are examples of side effects. Input from a file or from the user is also a side effect. Outputting to a file or to the screen is also a side effect. Side effects combined with aliases can lead to the potential for unintended side effects. For example, let's say we paint a house brown, and we paint house 2 hot pink, but we've forgotten that house and house 2 are actually two names from the same house. So when we try to print brown house, we end up with a pink house. A dangling reference is a usable reference to illegal memory. They occur when we have allocated, unassigned, or uninitialized variables, such as in this example here, we've created a pointer to an integer called x. However, we haven't used the new command yet, so it isn't really assigned space on the heap. It points to something, so it's dangling. Deallocated variables are also dangling references. Here we've allocated space for x on the heap, but now we've deleted x. If we were to use x after this, well, x would be a dangling reference. A dangling reference is not in itself an error. However, using a dangling reference is an error. Here, we create a pointer y, and then we assign 5 to that pointer before we've actually allocated space for that pointer on the heap. Here, we have allocated space on the heap for the pointer. However, when we delete y and then assign to y the value 5, there's no longer space on the heap for y, and this causes an error. Dangling references can also occur on the stack. In this example, we have a function foo and a global x. Inside of foo, we have a local variable called z and assign to it the value 10. We then make x point to the data inside of z. When foo is popped off the stack, x points to a no longer existing space. Dangling references can be dangerous. They can cause incorrect output when reading or writing to data that belongs to something else, and even a crash if the overwritten memory was running the program or, even worse, the operating system. Java is a lot safer than C++ because it doesn't have dangling references. In Java, if you try to access an uninitialized value or null reference, instead of grabbing some random piece of memory, you just get an error message. In this example here, we create a house called H, but we haven't actually made the house object. We've just created a variable called H. We try painting it blue. This will cause an error. Java will pick up on this and won't let you do it. Well, what if we create a house, actually create the house this time, allocating space on the heap for house object. Then we delete house too, and then try to paint it blue. Well, Java won't allow this either. There is no delete in Java. Java references all point to the heap, so the earlier example with foo won't work. You cannot have a reference to the stack with a pointer in Java. Another type of memory hazard is the memory leak. A memory leak is a heap memory that has been allocated, but the reference to it are lost, so it cannot be deallocated. For example, if we create a pointer x and allocate space on the heap for it, and then allocate a new space on the heap for it, what happened to the old space? Well, the old space allocated for it still exists on the heap. And now, because we don't have a pointer to it, we are unable to delete it. If we then went on to assign x null, we'd now have two spaces on the heap for x that aren't in use and can't be deleted and are just wasting space on the heap. We can also create memory leaks using functions. Here we create a pointer to the heap using new, but when the function gets popped off the stack, the pointer no longer exists, but the integer space on the heap still exists and no longer can be deleted because the pointer is gone. Languages with automatic garbage collection, such as Java, don't have memory leaks. Anything on this heap that doesn't have pointers just gets deleted automatically. Here's a couple of more types of memory hazard that are a little bit more rare. Consider what happens if we try deleting b here. We've created an integer a, we've created a pointer b, we get b such that it points to the data stored in a, and then we delete b. This could be happening either in globals or it could be happening inside of a function. The problem here is that a is actually not a heap object. And so when we say delete b, we are saying to the heap manager, please take this memory address and do with it as you will. We've given a memory location back to the heap manager that it has never had before and shouldn't have in the first place. This could cause the heap manager to get quite confused. Double deallocating is similar. It gives the memory location of A here back to the heap manager twice. The heap manager may now hand out this location twice if it didn't notice that there was a duplicate, creating an unintended alias with potentially disastrous results for your code. So, environmental hazards. An alias is when you have two or more names for the same data. Side effect is when a change with effects outside of current code. Aliases are only really a problem when there is unintended side effects. A dangling reference is a reference to unallocated memory. Dangling references aren't in themselves errors. However, if you try to read or write to a dangling reference, that will cause problems. Memory leaks are lost heap memory that you did not give back to the heap manager. Non-heap deallocation is when you give stack or global memory to the heap manager. Double deallocation is when you give heap memory back to the heap manager twice or more, since the heap manager potentially gets very confused and then hands it out twice or more. As you've seen from this video, C++ allows you to create all of these environmental hazards. Java only allows unintended side effects from aliasing. What about Python? Or the other languages you've seen in this course, like Bash or Prolog? What environmental hazards can occur in your project language?